Hello everyone, and welcome back to this next video in the Houdini Academy Foundation module. In this video, we are going to wrap up the balconies, and with that, also the procedural modeling chapter of our foundation module. So let's have a look at our example file and see what we're going to do today. So over here we have our building again. Let's move over to the balcony section here on the left. So if I look at the end of the network, you'll basically get the same result as what we have right now in our project. We have our building tiles, and we now also have these proto-balconies or basic grid shapes that are positioned on the outside of our building wherever our balconies are supposed to go. But they don't align properly, they don't snap together into corners, and also they don't have the proper shape and texture. So we need to set that up next. Over here, what we're going to do is we're going to take the building shape, that is the basic flat wall shape of our building, and we're going to project against that using our new balcony shapes. So if we take these and we first detect what parts of these shapes we actually do want to snap, we can do that with a bit of Vex. Then we can take that and snap it against the walls in order to position them and snap them around corners. Now with that, we will fix a lot of our issues already, but you'll notice that in some cases it does snap badly, and we need to fix that as well. So next, we are going to check if these points should have snapped, and if they snapped badly, we undo their snapping. But we do keep the ones that we do like these. And then finally, we need to do a little bit of final cleanup. So over here, we need to make sure that they don't intersect with the trims that are already on our building. So that's these shapes. Otherwise, we'll have intersecting geometry. And likewise, we need to make sure that in case our building is completely surrounded by balconies, we don't get weird issues. And that has to do with how whole polygons are dealt with in Houdini. And for that, I'll show you a quick example here. Let's say we have this polygon, a basic grid with a hole in the middle. If we were to create balconies and remove all of the edges inside those balconies, then we would get two polygons. One polygon for the outside of the shape and one for the inside, upside down. Now to some extent we already covered this earlier in the lecture, but here I'm going to show you how you can potentially fix this using a Boolean node. So over here I have a little subnet, and if we run it through that, you can see that we do create a proper polygon that can act as a whole polygon. And if we do this, then we can very quickly, using our extrude and texture nodes, give the elements of our balconies some depth, combine them together, and then finally output them to the rest of our building. So all of this isn't going to take too much time. In fact, we already dealt with most of the advanced stuff up here on how to integrate it into our tool. Now it's just about finishing up the integration of the balconies, so let's get to that. Alright, so the first thing that I would like to do is integrate a couple of data pieces into these balcony proto segments here, so that we can extract them at the end of our network, because we only want to extract our walls at the end of this for each loop, but we want to keep these proto segments separately so we can process them out for our balconies. So over here on the left, let's go into the loop, and I'm going to add a group in here. So I'm going to call this group the balcony floor group. It's going to be a primitive group, and let's just color it green. So now we should have a group come out of this node for our balcony floors, so we can identify those. Okay, then next what I would like to do is add some normals to our proto balcony shapes here, so that they have a left and right normal direction that I can use the raycast with. Because ultimately I would like the points of these balconies to aim towards their outside direction So if we grab this piece, for example, here, this one is going to aim towards the right, and on the other side it's going to aim towards the left. And that means I need to add some normal values to each of the points of this balcony shape. And if we do that for all of these, then they will have raycasting directions that we can use later on. Now, I'm not going to use a regular normal. I mean, I could, but if I do that, I'm going to have a normal, a point normal, attached to these, and I don't really want to do that because it would mess, potentially, with the vertex normals that we'll have later on. Now, I'm going to avoid that altogether, and instead create my own custom normal, so it doesn't mess with the visual of the shape. So over here, let's create a new attribute create node. Now I do want to see what I'm doing, so let's go to the end of our network. And in this case, I want to filter out, using single pass, one of the tiles that has a balcony on it. So in this case, I know it's 105, but in your case, you can always, of course, browse through your tiles to find one that has a balcony shape in it. And if you find one, then all you really have to do is go into your network and highlight the tile ID switch. That is before we copy it into place, so we have it sitting on the grid right here at the center of our world. Now, in this case, let me just hide those normals. What I would like to do is add a couple of normals pointing to the right and the left for each respective point. So for this grid, we have points 1 and 3, and they need to have a normal pointing in the X positive direction. So let's take this attribute create node and let's name it n_1. That's my custom normal vector attribute. And I tend to do this to debug or add custom normals. Simple enough. Over here, let's give it the name n_1. This is going to be a point vector. And let's also give it the point number groups. So that's going to be 1 and 3. And we need to specify this as points, of course, because otherwise it might mistake it for primitives. And then we just need to specify what direction we want the vector to be in. So in this case, that's going to be x1. So set value to 1, 0, 0. Now we can't see this vector, but it's very easy to retrieve. Let's just go to the info panel. And we can click on n_1. And if you do that, it will show it as a vector type marker, so you can see the direction of the vectors. And if your nomen gets in the way, you can always hide it. So let's do that. And then let's do the other side as well. Now in this case, we need to add a new attribute create node because we are dealing with a different group selection. Let's copy this. And in this case, I'm going to call it n_1 inverse. Let's say 0 and 2 instead. And then we can flip around our x value, and that will give us our normals pointing in each direction. Okay, so that's this part out of the way. We now have, for each tile in our building that has a balcony, the correct normal directions that we can use to raycast with. So let's go ahead and set up our balcony creation system. Over here, I first need to filter out if I actually want my balconies or not. So let's create a split SOP right here. I'm just going to grab this network, pull it down a bit, grab all of these outputs and plug them into the split node on the right. Plug that into the output of our for each loop. And then inside of this, let's specify what we actually want to filter out. Now by default, the split node is going to filter out on the left what we have selected. So over here, I'm going to specify balcony floor, and that will grab, of course, all of our grids. On the right, on the other hand, we'll still have our walls, and those have been untouched. Simple enough. So let's name this one split balcony shapes. And then let's go ahead and create a new netbox. So over here, let's drop one in. Make it nice and big. And let's call this one the Generate Balconies netbox. Okay, so let's first retrieve the type of data that we actually need. So let's create a null over here that will act as an input for our balcony shapes. So let's plug it up like that. And then let's also grab an object merge so I can retrieve some information from up here. Now, the section that I would like to grab comes right behind our copy floors with numbers node up here in the network. And for that, I'm going to create a new null node that I can sample from. So let's create one of those. Let's plug it up. And I'm going to call this one out walls. And because, of course, this is a node I'm going to reference, let me color it gray. And now we can simply grab an object merge and link it up. So I'm going to grab that. Let's call this one in for the walls. Color it gray as well. And let's sample our out walls up here. So let me grab that. There we go. So now there's a link between these two, just like we did before with the collision, for example. And you can simply grab this or copy it if you want down here. Okay, so with that set up, we now have all the information that we'll need to work on our balconies. Let's go and build this out. So the first thing that I would like to do is clean up my data over here, because we now have a lot of balconies that are simply disjoint from one another. What I would like to do is first clean this up, merge these points together, and potentially deal with any overlapping geometry that we might have. Now, I don't think we'll have any of that, but you can always do this fairly quickly using a clean solve. Let's create one of those. In this case, I want to consolidate my points so that we'll fuse them all together. Next to that, I also would like to take any overlapping primitives that we might have and remove those. Again, I don't expect to have any, but it's better to be safe than sorry in this case. And then I do want to make sure that I don't delete overlapping pairs. I always want to keep at least one primitive around, even if they are overlapping. That should deal with any of that. Then next, I'm going to use a Boolean node to join them together in case they are overlapping, like in this case. And we can do that fairly quickly using a Boolean union node. Now, all of these points, or grids in this case, are overlapping on top of one another exactly, which means that we should be able to use the Boolean node in union mode if we treat our inputs as surfaces. If we do that, then now they should properly overlap and mix together. Now, the Boolean node, again, does have some issues, but on flat geometry, it generally works pretty well. So I'm going to call this one Boolean union for the balconies. Okay, so next, let's go ahead and try to figure out, using a bit of vex, which one of these points we actually want to offset. Because some of them are fine to offset, but other ones, like, for example, these points here, we don't want to even try to offset these because they are already at a wall, right? We don't want to actually have our balconies insert into our building. So to prevent that from going wrong, we are simply going to filter out all of the points that we don't want to snap in the first place and only group the ones that we do. Let's go ahead and set that up. To do this, I'm going to sample my walls first to make sure that any points that are against the wall are going to be ignored. And we can do that fairly simply using a distance check vex expression called xyzdist. Now let's create an attribute wrangle here. And let's plug this in. In this case, I'm going to grab the main channel from my Boolean node here, and the second channel comes from the in-walls node. And let's call this wrangle node detect extendable balcony points. Now the first thing I would like to do is figure out the distance that we have for each of these points to our walls. Let's say that we take these walls here. If our points are too close, I want them to be ignored. So over here, let's type in gather data about points. And then I'm going to add a tab just to keep it clean. So let's go ahead and gather the distance for each of our points to the wall. Now we can do that fairly simply using the xyzdist vex expression. Now the xyzdist vex expression can do multiple things, but its simplest configuration is to retrieve from a point position the nearest surface in whatever input you give it. In this case, we are sampling from input 1, right here. So we can type 1, and then we can type in the point position that we would like to sample from our source geometry. That would be v at b in this case for the current point position. If we finish up this expression, and then we can write this to a variable, right? Let's say float dist to wall equals that. If we do this, then now dist to wall will retrieve the distance for each of these points to the wall. Now again, let's create a test attribute so we can see this. Let's say f at test equals dist to wall. And if I visualize that attribute, so let's create a test attribute here. Then now each of our points is simply going to return that value. Okay, that's pretty simple. If we look a little closer at these numbers, you can see that we have a lot of values that are either 0 or very close to 0. And that's because they are on top of the wall, and those are the ones we would like to filter out. Now I mentioned that the XYZ distance can also return other attributes. And before I continue, let me quickly show you how that works. Basically, in order to retrieve an attribute from a surface, just like how the ray node can sample information using the minimum distance function, the minimum distance method, we can also sample attributes from the hits on our geometry with the ray node, basically retrieving information. Now the XYZ distance function in Vex works fairly similarly. Basically what we can do in Vex is type in an XYZ function like this, where we specify the target geometry, then the current point to sample from, and then we can add to that the primitive that we hit, and then a UVW coordinate, a vector coordinate, on our geometry that we can then sample on this primitive. So I mentioned in the introduction module in the Houdini 101 series that every primitive also comes with a UVW coordinate. Now the UVW coordinate is simply a location on a mesh that is returned if you sample it with XYZ dist. Now the thing about the XYZ distance expression is that it can actually return more than one value. In this case, it's returning the distance to the wall, that's being the distance between our point and our target surface, but we can also retrieve the primitive and its UVW coordinate where it hit. But because we don't have these variables, this will actually error out. So if I were to write this one out, for example, let's say I write it like that, then in this case it's going to error out because we don't have a primitive or a UVW local variable just yet. We need to correct for that by first creating these variables so we can write into them. Let's say integer primitive, so we can sample the primitive number, right? and write it into an integer local variable called prim. And then let's also create a vector called UVW. If we do that, then now it has something to write into, and now this expression is actually returning more than one type of information. The first one, of course, is the distance, but we can also retrieve the primitive that was hit, if there was a hit, and then the coordinate inside that primitive. And if we combine these together using a prim UV vex expression, then we can also retrieve an attribute from that primitive. So in this case, we could retrieve, for example, the point position where our shortest distance was hit. So we can do that by writing the geometry that we want to sample, which in this case, again, is input 1, right, our wall. Then let's retrieve the attribute that we want to grab. Inside quotation marks, I'm going to grab the point attribute for the point position. And then we can type prim and UVW to fill it into this expression. If you do that, then now it will retrieve this attribute. We just need to write it out. So let's say I set it as the point position, v at p equals that. As a result, we've basically now snapped all of our points to the wall. Now, maybe we don't want to do that. So instead, let's actually retrieve the normal or the direction that these points would have snapped in. And we can do that instead by writing to the normal attribute. And then we can take this coordinate here that we retrieved, and we can subtract our current point position from that. If we do that, then now all of our points are going to aim at the closest location using a normal vector where they would have hit the other surface. So this is a pretty interesting trick. You can use this to find the closest distance using vex, get an orientation, get an attribute. Like we could also sample, for example, the point color, if there is a point color on this mesh, or any other attribute. So prim UV and xyzdist together can be pretty useful. Now it's important to note that the xyzdist expression is basically an omnidirectional raycast. Like I mentioned, it's similar to the ray node if you set it to minimum distance mode, right? Now the problem with omnidirectional raycasts is that since we're executing it over all of our points, if we have a lot of points, this might get a little heavy, especially if we're then also processing other code. Now Vex is pretty fast, and that helps us a lot. Plus it's also multi-threaded. However, if we want to speed up this expression just a bit, we can limit the maximum range that it's allowed to raycast in. And we can do that by adding behind this code here a distance. So if I set the distance greater than, say, 2 over here, which is our maximum range, let's specify it as 3, then all of our points are going to hit their nearest surface and we don't see anything change. But if I limit the range to, say, 1, then all of the points that are on the outside of our balconies here are not going to be able to find their primitive. And when that happens, this primitive value is going to return -1. -1 is not a primitive that exists, therefore it cannot retrieve a point position, which means it will return 0. Now 0 minus our current point position basically retrieves a vector that aims straight at the world center, right? Now to prevent this from happening, what you can do is wrap this expression here inside of an if statement. So we could say if our primitive attribute is not equal to -1, then we allow it to set the normal. As a result, now all of these points don't have their normal modified, but these ones do, even though we still retrieved all this information from them. But you will notice that they are currently retrieving a distance value of 1, because that is the maximum distance that it's allowed to check, and in this case these all return 1 because that's literally that value. What you could do is, in case we do hit a primitive called -1, we can specify, say, our dist to wall equals -1. In that case, we have a way to track if a point was actually allowed to hit something or not. Okay, so this is all pretty useful, but it's also a bit of a sidetrack. Now I just wanted to show you the power of the xyzdist expression. We will use this code in a minute when we need it, but for now I'm simply going to grab this and delete it out again. Go back to what we had before. Okay. And now let's have a look at what we can do with the distance to the wall. So let's write down here below a new section, and I'm going to call this one check which points should be grouped. Now in this case, if the points are within a certain range, I don't want them to be grouped. Okay, so in this case that would be if the distance to the wall is greater than 0.1. Now that's not going to help us with everything, but it will give us a good start. So let's write out a group here if this is the case. Let's say group underscore extend balcony edge equals 1. Now if we do that, then now under our point groups, we should now have a group here for all of these points. I'm going to filter out just these for a second. So let's specify it up here in the filter field. And there we go. I don't need to see this test attribute right now, so I'm simply going to get rid of that. Now, of all the points that we currently have visible, I only want to keep the ones on the outer corners of our mesh and not the ones that are inside of our mesh. And to do that, we can do a couple of things. First, let's measure how many neighbors each point has. So if we look at this, we can add a vex expression to sample the amount of neighbors for a point. We can do that using the neighbor count expression. Now the neighbor count expression is fairly simple. If we give it the geometry to sample and then the point number, it will retrieve for us how many neighbors are connected to that point by a line, right? So in this case we can retrieve it as integer attribute NBC for neighbor count. Now let's go ahead and output this again as a test attribute. So I'm just going to rewrite this one to NBC. Alright, so there we go. We can see this one has 2 neighbors, that one has 3, and this one here has 4. Now, in case we have a point that only has 2 neighbors, we are on a valid corner. So that one I want to filter. Let's say we add to this if statement by saying if it is further away from the wall than 0.1 and it is NBC equals 2. In that case, we now grab all the points on our corners and that should work just fine. Now there is one more edge case where this could potentially go wrong, and that is in case we have a diagonal attachment, like for example over here, where 2 balconies are injecting into one another at an angle. Their points have 2 neighbors, so they're valid, and they might potentially want to cast a ray. Now we can actually check if our points have a certain amount of primitives attached to them. In the case of this corner, we'll have 1 primitive attached to that point, but in case of these over here, we'll have 2. So we can sample for that. And we can do that by sampling the primitive numbers attached to this point. So this point would have primitive number 27 and 107 if we retrieve it from this point. Let's say over here we can add a new expression called point prims. Now point prims will retrieve all the primitives for a point. So we can specify for the current geometry and the current point number, point prims. Then we need to write this one to an integer attribute. In this case, I'm going to call it point prims. But this is not a standard attribute. It is an array-based attribute. And an array is basically an attribute that can hold more than one value, right? So we need to specify that by adding brackets behind the name, like this. Now, this will retrieve for us both of these numbers and store them into an array. It's a bit hard to visualize an array, but we can write it out to a string. So let's create a temporary test string here. And then I can visualize this by typing the sprintf or string print f expression in here. Let's add some quotation marks. And then I'm going to type %s, then comma, and then we can specify the pt prims local variable. And if we do that, then now if I were to visualize that attribute, so that is test string, we can now see the arrays and which primitives are part of each point. So here on the left we have 23, this one has 23, 24, and here we even have 4, 27, 107. Okay, so that's these three, because they're attached to that point. Now in this case, I don't actually want to sample the primitive numbers themselves. I simply want to retrieve how many primitives are attached to a point. And to do that, we can grab our pt prims array and we can sample its length, basically how many elements are in that array. To do that, let's create a new local variable called pt prim count. Now to do this, we can sample the length of the array by using the len expression. Now the len expression returns the length of an array. It's fairly simple actually. We just need to specify our pt prims attribute, like so, and that will do it. Now if I were to output that as, say, my test attribute, then we can see this point has 3 neighbors, that one has 2, and in the corner we have 1 primitive neighbor. Now just to let you know, you might have noticed there is a length expression. That one actually returns the length of a vector, not the total amount of entries in an array. So just keep in mind, len and length are not the same. So now that we know how many primitives are attached to a point, let's just add it in here. Let's say if the pt prim count is equal to 1, then we allow it to make a group, otherwise we don't. So as you can see, we now have only our groups on the corners, not near our walls, and not in the middle of geometry like in this case. Okay, so that's quite a bit of vex that we just wrote. There's a lot of other vex commands that I could teach you. The xyzdist, for example, only samples in an omnidirectional range. We could also use the intersect vex expression, which acts more like a standard directional raycast. However, that's not really the point of this lecture. I just wanted to show you a couple of expressions that we can use to sample information. And we'll get to this more in the next module of the masterclass. Now for now, let's go ahead and hook this up. So now that we have this group, let me just grab this network, move it over a bit. And what I would like to do is now raycast these points that we added groups to against a raycasting collision geometry. At this moment, we don't have anything to hit against. We have our walls, sure, but if we were to cast a ray from these points, it wouldn't actually hit anything. So to make sure that that does happen, what we can do is create a collision geometry that extends outward from each of the corners of our building. So let's do that first. Let's grab our walls over here. And what I would like to do is add a new vector that points outward from these wall tiles. So I'm going to use a facet node for that. Let's plug that in. And I'm going to use this one to retrieve the normals for this mesh. We can do this using a variety of methods. This one is just easy to set up. We only have to specify post-compute normals down here. If we do that, then now all of our meshes are going to point outward. And if we have two primitives over here, they will average together and output right there. Now next, I would like to identify which of the edges on our building, which of the points, should actually create a collision mesh. And we can do that again using a group node to identify the corners on this building. So let's create another group node. I'm going to call this one group corners. And in this case, I would like to group the edges of our building. Let's call it corners, by the way. And down below, let's set up by edges as minimum edge angle of 1 degree. Now if we do that, then we should grab almost every single edge unless the angle is smaller than 1 degree. I think this should be safe enough. Okay, so now that we have this, let's go ahead and create a poly extrude node so we can extrude these outwards. Now I'll show you two different ways how we can use the poly extrude to extrude these edges. First, we can use the simple analysis of the current surface by just grabbing the edge group up here, our corner group, and then we can extrude it outward. So we just give it a distance. Now if we use the distance value, it will in this case use the primitive or edge normal that's currently present on our geometry. Technically, if we don't have this normal, it would still work, okay? Because it will grab it from the geometry just like this facet node is doing right here. It's basically computing it for you. However, in case you want to set it yourself, you can also use, for example, the point normal and then specify it as an existing attribute. If you do that, it will use the existing normal or a custom normal if you want to. So let's set this over to existing in this case. Now, like I mentioned, this is not per se necessary, but it is a way to do it, so I just want to demonstrate that. And let's name this poly extrude node, before we continue, extrude corners outward. Now, these shapes that we're creating here are basically collision shapes for our points to raycast into, right? So let's have a look at that. Here you can see, now we have something to hit. However, the distance of these collision shapes needs to be at least twice the actual balcony depth. If you set it higher, the balconies can be deeper. But you do have to keep in mind that by extruding these out, you are creating something your balconies could hit. If your building has a particular shape, like a U shape or something, you don't want these to extend too far, because it might cause collision issues. It might cause errors. So I'm going to limit how far they can extrude by up to 2 times the balcony depth. Let's grab the balcony depth parameter. That would be over here. Let's copy that. And let's plug it in and multiply it by 2. Okay, so let's set up our raycast next. Now we could do the raycast with Vex, but frankly it's a bit unnecessary. Let's in this case just use a ray node instead. So the ray node, as we've used before, we can simply plug it in. And what I would like to do on my ray node is specify that normal. And we can set this over here under direction from. So let's set this over to attribute. And then instead of using the normal attribute, we can specify our custom normal n_1. And that will now allow all of our points to raycast all across our building. Except, as you can see, currently all of our points are raycasting, and that's not something I want. So let's fix that. Over here, let's specify our extend balconies edge group. If we do that, then only our points that are marked as such will snap. Then next, let's have a look at points we don't want to snap. For example, here we have one that's snapping way too far. Let's set this one up so it can only snap at a maximum distance, similar to how we dealt with it with the XYZ distance system before. I'm going to turn this on, and I'm going to plug in the width of our tile over here. So let's grab that under the building settings. Let's grab our wall segment width. Let's plug that in here. And then, because these tiles can actually stretch a bit, plus I do want them to be able to work their way around corners, I'm going to boost this to 1.75. And as you can see, this does allow it to snap around the corner. Now again, using a value like this is a fixed value. As a result, if we create balconies that might either be just too big, or our wall tiles or our corners are just slightly wrong, maybe this value isn't enough, and then it won't snap. As I've shown you before, if we take, for example, these balconies and we make them too big, then it might not work properly, right? If we make the balconies too deep, for example, let's say a size of 5, it might not snap, and in this case they don't, though in this case they do. So it just depends on the angle and depends on the distance. Now you can play with this value if you want, but I suggest you don't set it higher than 2, in fact, because you don't want the wrong tiles to snap, okay? I think this is as far as you can go safely. Alright, so let's call this one the Ray to Extended Balconies. And with that, we now have this set up. Now next, we need to fix some of these points here, because as you notice, some of these points are snapping to a non-existent balcony. Let's correct that. First, let's fuse together all of the points that were just snapped. For example, here are 2 of them, as you can see. Let's create a fuse node, plug it in over here, and that will fuse all these points together. Now next, let's create a wrangle node, and again measure how many neighbors each of these points have. So let's create an attribute wrangle. And let's call this one measure neighbors. Now in here, let's just say y is NBC equals neighbor count, and then 0, ptnum. That will do. So now we should have an NBC attribute in here, right there. So with that, we now have this attribute available. Let's visualize it. Let's open up our panel. Let's grab NBC, and let's change it into a marker instead of a color. So let's do that. Okay. So let's see what we can do with this. Let me just quickly hide all this stuff so it's not as cluttered. And also let's hide these other attributes that we're visualizing because, well, we're not using them right now and they will just change the offset of our visual. So we have this point. This point was just snapped and now it has 3 neighbors. So we don't want to change that one. This one is correct. This point here, on the other hand, number 2, was not snapped to another balcony, so we don't want this one to be offset. And likewise, if we have, say for example, 4 or 5, we don't want those points to stay. We only want points that were fused together at corners with a value of 3 to remain. So let's create an attribute transfer, because I don't want to fuse these points together just yet, because I can't move them back if they've been fused, right? So let's grab our original geometry. Let's create an attribute transfer. And I'm going to transfer the neighbor count attribute, which is a point attribute, at a very small distance of 0.001, right? Because ultimately these points are overlapping, so that should be fine. And let's call this one the transfer NBC. So with that, now we have our attribute available, even though our points are not fused, as you can see. Now let's undo that offset. Now, in order to undo the offset, I need to know how far each of these points was actually moved. And we can do that in the ray node by sampling the ray distance as well. So over here under the ray node, let's go to point intersection distance and let's turn that on. If we do that, then now we should retrieve over here a distance value. Now all the points that were snapped will have that value, and we can use that to then return it back to its original position. Next, let's create an attribute wrangle. And I'm going to call this one undo offset on unsnapped edges. So let me first write a comment here. Let's say if we didn't snap or snapped badly, undo the offset. Alright. Now I only want to apply this to our actual balcony points, the ones that we were extending, right? Up here, let's grab those. So we will only consider moving these points back if they are in this group. And then in here, let's say if our NBC attribute is not equal to 3, then inside curly brackets, let's set our point position back. Now we can do that by taking our original point position. I'm going to say minus equals, because I want to subtract back from our point position, right? The offset. I can use the vector at n_1 attribute for that. And then we can simply multiply that by the distance value that we're getting from this ray node. Now, just in case our normal_1 vector is not normalized, or rather a value of 1 length, we can normalize it using the normalize command. So let's do that. It's always good to normalize your vectors before you use another value to multiply them, just to be safe. Okay, so with this, we now have offset our points back, and that should deal with that. So now we can fuse them again, because now they should be all in the correct position. And we should only have points that are wrapping around corners snapped up. Let's create a fuse node. Let's call this one fuse balconies. And with that, we now have our balconies properly wrapped around corners. Nice. Okay, so at this point we now have our balconies wrapping around corners, but they're still a bit dirty. So let's have a closer look here. As we can see, the intersection of these segments is creating a weird internal polygon shape, and we also have it slightly sticking into our building. I don't want that, so we need to clean that up. Now what we can do is we can actually take our building floor and our trim, which should be over here, and we can subtract from that. Because ultimately we don't want our balconies to stick into our trims, and if our trims get deeper, which we could do of course with the settings over here, our trim thickness, then we also want that to be subtracted as well. So let's deal with that first. Now, what I'm going to do is I'm going to actually sample over here from our copy floors node. So let's retrieve this data here. Let's create a null node. I'm going to call this one out trim edge. Now we're actually going to grab a bit more than the trim, but that's fine. And then let's grab a object merge and hook this one up, just like we did before. Let's call this one in trim edge and then reference this one, so we have a link. Let's pull it over. And then next, what I would like to do here is actually subtract using this mesh from that mesh. And I'm going to use a Boolean node for that. Let's say we grab a Boolean subtract node. Let's grab our left channel here and then plug it into the right for our trim edge. If I subtract one from the other, most of the time, this is probably going to work. We are currently evaluating the mesh here as a solid, but we are also evaluating this mesh as a solid as well. And this is not a solid, this is actually a surface. It doesn't have any depth. So just in case, I'm going to set this Boolean node over into treat as surface. Now that will work again. However, just in case, if say there was a slight offset between these two, like if for whatever reason our system was going to have a little bit of imprecision, and Boolean nodes are very precise, okay? So if there's a slight difference between our inputs in height, even if it's just 0.0001, like that, it might fail. So just in case, to prevent this from going wrong, I'm going to treat both of my inputs here as a surface, and then I'm going to make sure that both of them are snapped to a reasonable integer. Let's use the same trick that we used before again to round the value. Let's create another attribute wrangle node. And I'm going to call this one snap height by tolerance. And then to snap it, we can simply say v at p dot y for the height of this mesh is equal to rounded integer of v at p dot y, multiply that by 1000, and then afterwards divide it by 1000. Then we're effectively rounding it to the third decimal. If we do that for both these meshes, then now they should be lined up. So if we have a very, very small difference in height, it will be corrected by these snap nodes right there. That's just in case this goes wrong. Like I said, Boolean nodes are very precise. They have a very high precision level. And if your meshes even differ slightly, you could get slivers, you could get weird issues. I want to avoid that. So let's set it up like this. Let's call this Boolean node subtract trim, like that. Now, just to be clean, let's run this over another clean node, just in case the Boolean has resulted in some kind of bad geometry, maybe some degenerative geometry, some zero space surfaces or whatnot. The clean node will try to clean that up for us. So let's just hook it in like that. Alright, so at this point we now have our balcony shapes and they are being subtracted with the trim. Let's go ahead and clean up these internal edges as well, give it some better topology. Now to do this, we could use a divide node. The divide node has the ability to remove internal edges, only keeping the outside points, right? If I remove shared edges, it will clean it up. However, this will break the moment these meshes wrap around the entire building. If I grab my balcony interval and I set that to the same as the width, Now we'll have balconies around the entire building. We effectively create a whole polygon. Now, like I was showing you before in the example, a whole polygon is basically a polygon that has all of its edges blasted away. So in this case, you could say we use the divide node here again. And as a result, we now have two polygons. They are aiming in opposite directions. Basically, the original shape will be pointing in the original direction, but whatever was an interior hole shape will now have a new primitive pointing in the opposite direction. Now we can account for that and fix it using a little system that I'm going to build now, using this system. So let's go back to this over here, and let's grab this divide node, and I'm going to wrap it inside of a subnet. And let's call this one remove internal edges. I'm going to make this one yellow. And then inside this network, we should already have it hooked up for starters. I'm going to simply remove my shared edges like before, but then I want to filter out all of the primitives that are upside down. We already have this code in our system, so we can grab it or we can rewrite it. Let's just quickly rewrite it. So I'm going to create a normal node and set it to primitive normals. So we have a normal on this. And then let's grab a group expression node. And this one's simply going to grab inverted prims. Let's say group inverted prims. Over here, inverted is the case if our v at n.y is less than 0. So if the normal of the primitive is less than 0 in the y direction, then we'll simply group it. Then let's grab a split node. And with this, of course, we can split apart these, so we can grab the inverted group, which will come out on the left by default. I'm going to invert this. So the left channel is going to be my main floor, and then the right channel is going to be the whole polygon. So we can grab a null, so we can see that. Let's say whole poly. And then we can simply grab a Boolean node to subtract them from one another again. So let's grab a Boolean subtract, plug that in. And in order to make this work properly, we need to set them both to surface mode, because we are subtracting surfaces from one another, not solids. And that will create a new polygon, which has a connecting line over here, somewhere in the mesh, that will allow it to be a whole polygon. Now we still have all this point data, all these access points everywhere. We might not need these. So what I can do is I can remove those, of course, using a facet node. Let's remove the inline points. Let's say facet clean inline points. And that will work for the main mesh, but we might also want to do this for the whole polygon as well. So I'm just gonna plug that in. That will create a clean mesh for us. Now you don't need to per se remove the points. I have noticed that in some cases the Boolean node might fail. Like here, for example, it hasn't properly cut the shape, and that has to do with the points being aligned in a grid. This might not be the case if they're slightly offset in X or Z, but removing the inline points in this case will fix that. So I'm just going to integrate it here as well. Okay, so let's output this to an output node. Always a good idea to put an output node in your subnet, just to make sure this one calculates out no matter what is selected here. So with that, we could take this and run it over, say, a divide node that will triangulate these meshes properly. So with that, we now have our balcony floors. We can now extrude them up. So let's go ahead and find one of our extrude and texture nodes, which will also triangulate it if we let it. Up here under our create floors, we have our extrude and texture node for the floors. Let's copy this one because it's already set up almost correctly. Let's grab it and let's plug it in down here. Okay, so let's have a closer look. Over here we can see we do have our materials, but we do have a problem. And I've noticed this is because we already have a UV on this mesh. And the sweep node inside of this system isn't properly overriding that UV. We need to correct for that inside of the extrude and texture node, just to make sure it always works. Now let's quickly open up the side-by-side view, and you might see in here we have a small little box down there. If I look at that one, we actually already have some UVs. We have vertex UVs coming into the node. I do want to make sure this works, so let's go into the asset, open it up, and then here where we have our sweep, I am simply going to remove whatever UVs are already present on our mesh. So let's create a attribute delete node, plug it in, and over here under vertex attributes, let's remove that. So let's give this one a name, clean UVs, and now this should have dealt with this issue. So there we go. We now have our UVs properly projected. Let's go back outside. Save this one up. And let's close the asset. So this will have updated everywhere, and we shouldn't really have to worry about this because ultimately we were creating a new UV anyway. No need to worry about existing UVs messing up our result. Okay, so that's a little bug we had to squash. Let's go ahead and set up our actual materials. So under textures, for the top UV, I want to change my granite floor tiles over to the balcony tiles, which should be in here, like that. Make sure you change both, right? And these are a different type of brick, basically. Now as for their layout, we'll keep this one the same as the other one. And with that, this one should be set up correctly. Okay, so at this point we now have our balcony surfaces. But before I go ahead and hook this up to the rest of our network, let's also create the railings. Now the railings can be extracted from any of these surfaces, except if we grab it from our final cleaned geometry, like say our internal edges here, we've already removed a part of it. And if I try to extract the railings from that, then they won't completely reach to the walls, as these surfaces don't actually reach the walls. So instead, I'm going to grab them from up here, from our fused balconies node. Now this one hasn't been cleaned yet, but that's not a major problem. We can work around that. Let's grab a poly extrude node first. Let's plug that in. And let's call this one poly extrude inset. Now in this case, if I were to inset this surface, you can see I'm creating a mesh. I'm creating an edge, basically. So let's output only the sides, not the front. This will output a nice railing shape for us. Now we still need to clean this up. So let's hook this up first. I would like to be able to control the thickness of my railings. So let's go into the type properties. And over here, under the balconies tab, let's just copy the railing height. I'm going to copy that and then paste it up here under balcony depth. That will put it in between. Now it's going to be called railing height 2. Make sure you grab that one, not the original. And let's rename it to railing thickness. Now I do want the railings to have a minimum thickness of 0.1, just like the other one, but a maximum size of 1. Now I'm not going to lock that, but I suggest you leave your railings at a thickness of 0.2 by default. So if you set that up, then accept that. And then let's just grab it from the interface and hook it up. So over here, let's plug it into the inset. Now with that, we now have a proper balcony that we can control the depth from, and it should always have at least some depth. Now it won't allow you to intersect it too far. It will eventually hit the center, but don't worry too much about that. Basically what we need to do next is clean up any of these balconies that are on the walls. And also, let me just quickly return these balconies back to how they used to be. So I'm going to change the width back to 5, so that's lower than the interval. So we have some nice shapes over here, right? We have some edges. Let's say we look at one of these. What I would like to do is have an edge that goes around the front, along to the sides, but isn't at the back. And right now we do have that. We can remove it using the XYZ distance again by sampling the center of each primitive and checking how close that is to the wall. So let's create a new attribute wrangle node, and let's also grab a line from up here. Let's grab a dot with Alt. And then let's hook it into an attribute wrangle. Let's plug the primary input into the poly extrude and the secondary into the input from our wall shape. And let's call this one remove segments on walls. So what I'm going to do is use the XYZ distance again, but this time from the center of each primitive instead of the points. Let's change this attribute wrangle over to primitive mode. And then in here, let's type if xyzdist coming from input 1 to the current point position. So that will grab the center of each primitive and then sample how far it is from the wall, right? That will return a value. And then we can simply compare what value it returns with the thickness of the railings. So we can use a parameter for that. Let's say channel reference float, railing thickness. If that is true, if the distance to the wall is smaller than the railing thickness, then I would like to remove this primitive. So we can do that using the remove primitive vex function. Remove prim. In this case, we need to specify the current geometry to remove, which is always 0. And then the primitive number to remove, so primnum. And then finally, if we want to remove any points that belonged to that primitive, in this case we do want to do that, so we specify 1. If we set this up, and if we boost this value up a bit, you can see that we start to remove the sections of our railings that are on the walls. Now, I don't want to remove them if they're too far from the walls, like these side pieces or the front. So let's hook it up so it only takes the current railing width into account. Let's grab the railing thickness. Let's plug that in. And I'm going to set it up so it's slightly bigger than half the railing thickness. So let's say 0.51. Now this will mean that if any of these railings, their center point, is within slightly more than half the distance from the wall, then it will remove it, right? Simple enough. Now that will leave us with proper geometry for our railings. However, we still have these edges here, these points that aren't snapped properly. And I do want to clean it up as well. So let's create another attribute wrangle node. Let's grab the main input from here and then plug it into the second input for our walls, just as before. Now let's call this wrangle node the snap railings to building. And what I would like to do here is check if these points are close enough to the wall, and if they are, then we're going to snap them to the wall. Now once again, we could use a ray node to do the same thing here. We don't need to use a vex expression, right? Because the ray node could do this for us. If I grab a ray node and I plug it in, and I set this up as a minimum distance, and then limit the maximum distance value, then it will do the same thing. So if you want to do that, go ahead, okay. However, in this case, I'm going to write it out in vex. And I already showed you how to do this. If you remember, you should be able to do this yourself already. So over here, let's write a xyzdist expression. We need to grab the distance value, so let's create a float called dist. And then inside the xyzdist, let's sample from input 1 from our current point position. And because we need to also retrieve the location that the point hit in order to snap to it, let's grab the primitive and the UVW coordinate as well. Now in order to make that work, we need to create the integer local variable for the primitive and the vector local variable for UVW. So this will read that and write it out. I'm not going to limit the maximum distance. I don't want to worry about that. All I need to do at this point is say if the distance value is less than a particular parameter, in this case that would be the railing thickness again. And if we then multiply that by say 1.1, that should be just enough to make sure that any of the points that are extruded inward are going to snap back to the wall, okay? Then inside this if statement, we can then simply say v at p equals the prim uv function. We're going to grab the point position attribute from our input 1, and then in order to make this work, we need to also provide the primitive and the UVW coordinate so we can properly extract the value. So let's go ahead and plug this up. Over here, we can now set the value high enough, and there we go. We can now snap properly this point to the edge. Now we do need to hook this up to our railing thickness, so let's go ahead, grab that, and there we go. This should now properly snap all of our railings to the walls. Alright, so we are almost done with the balconies. Let's just finish this up. First, we need to set them so they are on top of our current balconies. Now this should be pretty simple. We just need to grab the floor thickness, which is used for the thickness of these guys here, and boost it up a bit. So let's create a transform node. Let's call this a raise on top of balcony floor. And let's grab the extrusion value like that. Okay, that's one. And this might overlap a bit, but again, that's because we are putting this on top of our trim edge as well, like that. Okay. Okay, so next, let's make sure we clean this up properly. Once again, if we were to have balconies that extend all the way across our building, this might break if we try to clean it up. So before we do anything, let's grab a copy of our remove internal edges node and let's plug it in over here. Now this will also get rid of any of the internal points. That will give us some cleaner geometry. And then next, let's give it some depth. And then Now for that we already have a node that is properly configured. So let's go up to the top, go to our roof railings, and let's just copy this node. And there we go. This should now be properly set up. We have our texture, we have our UVs, and there we go. We now have a proper textured balcony. Now I'm going to rename this node to, let's say, balcony railing, right? And with that, we have this set up. So let's go ahead and plug this together. I'm going to grab a merge node. That should give us our balconies. And just to make sure everything is working, let's set it back to individual balconies instead of merged around. So yeah, all of this looks fine. Okay. So with this, let's go and output it. So let's copy once again one of our networks over here. Let's say this one. Let's plug it up. And this should properly, bevel it, make sure we clean it, and let's give it a color. Let's say we make this one 0.2. Something darker, perhaps. All right, so at this point we are almost done. We just need to hook it up to the end of our network, and I'm gonna do this with a switch, so I can turn the balconies on or off, and that also will include the ability to turn off the door generation for the balconies, because ultimately it wouldn't make any sense to have a door if there's no balcony, right? We don't want anyone falling out of the building. That would be a bit tragic. Let's set this up. Let's open up the type properties, and then under the balconies tab, let's add a separator over here and a toggle. Now let's call this one spawn balconies. I am going to turn it on by default. So let's go ahead and apply this. And now we should have a toggle here. Now in this case, if the balconies aren't spawned, I don't need these settings down here, the ones for the balcony positions and the door positions. So let's gray these out if this is disabled. Let's go in here, let's copy that, and let's just start setting this up. So disable when balconies are 0. And then we can just copy that to the disable when flag of all these other parameters as well. So we can leave the separator alone. There's no point in disabling that one. That should be fine. The railing thickness, let's also gray this one out, because it only applies to the balconies, not the top roof railing, right? And then we can accept that. Okay, that looks good. So let's just hook all of this up, and then we can finish up this lecture. Let's create a switch right here. And let's call it enable balconies. Let's plug this in. And let's give it a null in case it's disabled. So that will be input 1, right? Like so. Okay. And then let's plug it up top. So it's part of the main input. If you want, you can of course move everything down a bit. It's really up to you how you want to do your spacing. Personally, I like to keep things top to bottom, right? So it's clear enough. Next, we also need to hook up the collision. So over here, this is before we run the triangulate node and the bevel. Let's copy one of our collision nodes from somewhere in our network. And just like before, this should give us a unique number, so we can copy that. And let's plug it into our collision node. So we just add that one to the list. There we go. We now have a collision geometry version of this. However, it doesn't actually remove them if we turn off our balconies. So let's grab this value and let's also plug it over here into our merge, so we can disable this merge entry for the collision. That will do fine. And then finally, just in case, as you can see, if we have our balconies removed, we need to remove the doors as well. So up here, under the balcony door group, I'm going to disable this entry if we don't have balconies. So we can just plug that in, just like the other one. And then if we do spawn our balconies, then we'll have our doors. Otherwise, we won't. All right. So at this point, I think we are done. Let's just quickly test it out. So here's our render. We do have our balconies. They are sitting on our trims. So we can grab our trim, for example, and make that a bit thicker. All right. So that seems to work. Maybe we can make our balconies a bit wider, right? Balcony depth to 4, maybe. Again, as you can see, this might break if you set it too high, but if you don't boost it too far, it will work just fine. And then finally, let's say we make our railings a bit thicker. Okay. And these are separate from the top, right? This is the wall thickness, that's the railing thickness. If you want to change that, then, well, you can do so up here. All right, so at this point, we're pretty much ready, I think. Let's go ahead and bring this into Unreal. Let's go ahead and test it out. So I'm going to save my asset. Again, make sure you are rendering the output node. Save the scene. And then in Unreal, let's import everything again. Now I did, once again, make a change to the extrude and texture node. So I'm going to grab all of the utility nodes, re-import those, rebuild, actually. Okay, so there we go. We now have our balconies properly added to our building. Let's have a quick look. So we can see they are properly wrapping around the corners. And if we press play, let's find one. Here we have a door. All right. So we can now, well, scale our building or jump down if we want to. That all works fine. Now with that, we have pretty much wrapped up the modeling component, the procedural modeling chapter of the foundation module. And we are almost done with the foundation module as a whole. Because at this point, these tools are indistinguishable from one another. Our own tool will now do the same thing as the example file, except for one thing. The example file, at least version 1.1, that I'm going to distribute after the next chapter, is slightly faster than our tool. And that's because our tool hasn't been compiled yet. So that's what we'll do in the next chapter, which is not going to take too long. We just need to move a couple of nodes out of the loop that creates the tiles on our building, such as the material nodes and the extrusion nodes. And that's going to be all about optimization. Make the tool a bit faster and how to do that. Okay, well, I just want to say well done. Because at this point, you have the entire building complete, all the models are complete, and you've covered a lot more VEX. Now the vex that we covered in this video isn't too complex, but for a beginner it's still a step up, okay? So we are going to cover a lot more complex vex in future modules of the masterclass. I will cover more about this at the end of this module, at the end of the foundation lectures. But for now, thanks for watching this video. I hope you enjoyed it. I hope you learned a lot from it. And now you have a proper building that you can work with. I would love to see what you've come up with. Please go ahead and leave a comment or a like. It always helps out the channel. And if you want to show off your work, come join us in the Discord channel. Links are in the description below. I always like to see what you guys come up with. So thank you for following along with the course. And I hope to see you in the next video, where we're just going to optimize the tool, make it a bit faster. Okay? Thanks for watching and have a good one.